This is going to be a short review of how we're predicting products. I'm going to start off with a couple of these smaller earlier reactions. By looking at these, we can tell that they're synthesis because we have one element reacting with another element, and that was what we had for synthesis, two elements reacting to form a compound. In order to figure out what we're producing, we're going to look at each element and what ion it would make. So we have calcium. Calcium is an alkaline earth metal. You look at the periodic table, and it is a 2+ charge. It's going to be reacting with nitrogen, which, as an ion, it's an anion. It's in the nitrogen family, and it is a 3- charge. So when we look at these things, we need to use the charges in order to figure out how many of each ion is going to be in the compound. So if we have Ca2+, N3-, we're going to end up with a few more Cas. That makes it 4+ and 3-. That's not good enough. Let's see, that would be 4+ and 6-. Add another calcium. That gives us 6+ and 6-. So with Ca3 and 2, we have a total of 6+, 6-, overall neutral compound. The next thing we're going to have to figure out, though, is whether or not the entire equation is balanced. Equations have to be balanced so that the law of conservation of matter is upheld. You can't create, you can't destroy matter. So looking at this, the calciums, we have 1 on the reactant side and 3 on the product side. So if I put a coefficient of 3 in front of the calcium, I have 3 calciums on both sides. Now nitrogens, I have N2, I have 2 N's on both sides. So with 3 calciums and 2 nitrogens on both sides, that is balanced. So 3 atoms of calcium would react with 1 molecule of nitrogen to make 1 unit of Ca3N2. Alright, what if they don't give us the formulas? What if they just give us the names? So the next one says barium reacting with oxygen. So we have to look at that and say, what's barium? Well, barium is Ba. Right now it's just an element, so there's no charge. Reacting with oxygen. Well, oxygen was one of those diatomic elements. We remember the Hankelbrief, and that means that it's O2. So barium reacting with oxygen is Ba plus O2. Now we look at this and say, ooh, element, an element. It's a synthesis reaction. So I'm going to take these two things, figure out what ions they are, and put them together to make a compound. So we're going to have Ba, which is 2+, oxygen, which is 2-, and since you already have 2+ and 2-, we only need one of each. So we end up with the nice formula of BaO. But now we need to balance our equation. We look at it and we got 1 barium on the reactant side, 1 barium on the product side. That's good. But we have 2 oxygens on the reactant side and 1 oxygen on the product side. So we would need more oxygens on the product side. If I put a 2 in front of this, 2 oxygens on the product side and 2 oxygens on the reactant side. So now it's balanced. 1 atom of barium reacts with 1 molecule of oxygen to form 2 units of BaO. Now for a different kind of reaction. Looking at what we have here, I see that we have a bunch of carbons, hydrogens, and a little bit of oxygen there. And this is reacting with O2. So if we have carbons and hydrogens reacting with O2, we know it's a hydrocarbon combustion. Whenever we have a hydrocarbon combustion, the products are always the same thing. They are always going to be CO2 and H2O. So if we can memorize that whenever we see carbons, hydrogens reacting with oxygen, that it makes CO2 and H2O, that makes these easier. Now we just have to go through and balance them, which can be a little bit more tricky for these. When we're using the hydrocarbon combustion reactions, we always want to balance them in the order of C, then H, then O. C, H, O. So over here, we have 2 carbons. We have a total of 6 hydrogens because we have 5 here and 1 there. So we have that. We also are going to have oxygen all over the place in this equation. So what I recommend is keeping track of oxygens up here. We've got 1 in the C2H5OH, and we have 2 in the O2. Right now that gives us 3 oxygens. So on the product side, we have 1 carbon, 2 hydrogens, and we have 2 here and 1 here for the oxygens, giving us 3. Alright, so you always start with carbons. We have 2 on the reactant side, we have 1 on the product side. In order to balance this out, we're going to put a 2 in front of the CO2. 2 times 1, we have 2 carbons. 2 times 2, we have 4 oxygens in the CO2. We still have the 1 oxygen from the H2O, giving us a total of 5 oxygens. Carbon's good, hydrogen's next. On the reactant side we have 6 hydrogens, on the product side we have 2. Any number that I put in front of H2O is going to be multiplied by 2. So if I have a 3 in front of the H2O, 3 times 2, 6 hydrogens. 3 times 1, we're going to have 3 oxygens over here, added to the 4 we have from the CO2, now we have 7 oxygens. Alright, in order to get our oxygens balanced out correctly, we are going to have a total of 7 oxygens on the reactant side. We don't want to mess with the C2H5OH because then that would change everything. So we already have 1 oxygen. So we're going to need to have only 6 from the O2s. So what could I put in front of O2 that would make 6 oxygens? 3. If I put a 3 there, oops, wrong color. If I put a 3 there, 3 times 2, 6 oxygens, plus 1 over here gives me 7. So now I have 2 carbons, 6 hydrogens, 7 oxygens on both sides, and overall it's balanced. What we end up with is, for every 1 of C2H5OH, you would need 3 molecules of O2, and it would be producing 2 molecules of CO2 and 3 molecules of water. So that's a hydrocarbon combustion. You see carbons and hydrogens react with oxygen, always making CO2 and water. And when you balance it, make sure you do carbon, then hydrogen, then oxygen. Otherwise, it takes you a lot more work to do it. Alright, moving on to another one. So the last kind I have over here is going to be a double replacement. The reason that I can tell it's a double replacement is because I have a compound and another compound. Having 2 compounds is how you identify a double replacement. What goes on here is that the ions are going to switch partners. Right now we have a positive calcium and a negative chlorine with a positive sodium and a negative phosphate. The only other option for these things is to have the calcium switch what its partner is. So right now chlorine is attached to it, but if we instead replace the chlorine with a phosphate and move the chlorine over to the sodium, we're going to have 2 different products. So the first thing we do is we switch our ions. We're going to have the calcium, which is an alkaline earth metal, so it's 2+, and we're going to have it with PO4. Different ways you can remember what the charge of PO4 is. You could either look back at your polyatomic ion list, or with the new solubility table, if you look at that, you can see that PO4 right here has a 3- charge. So different places to look for it. Put that away for now. So our PO4 has a 3- charge. Alright, so if I have a 2+ and a 3-, they're only going to work out right once I have a total of 6 charge. So if I had like Ca2+, another Ca2+, that gives me 6. Add another PO4 3-, 6+, 6-, that would be good. So that will give us Ca3PO4 2. Alright, now for the next product. For the next product, we are going to be putting Na plus 1 with Cl minus 1. Since it's plus 1 minus 1, we end up with NaCl. The next thing we need to do is look at our solubility chart and figure out if either of these things are solid or aqueous. We're going to need to have our little states of matter parentheses, and then we're going to go back to our solubility chart and take a look. We will start with looking at calcium and phosphate. So we find calcium, and we move over until we get to phosphate. There's an S there, so that means that we're going to have the state of matter of solid for calcium phosphate. This one should be obvious, but if you have sodium and chlorine, we're looking at table salt here, and that is aqueous. A little aqueous there. Kind of hard to read, sorry. Alright, the last thing that you have to do for a double replacement reaction is balance it. So let's look at what we have here. We have 1 calcium on the reactant side, 3 calciums on the product side, so let's put a 3 over here, 3 calciums and 6 chlorines. We have over on the product side, we have 3 chlorines. So if we put a 6 there for the chlorines, now we have 6 chlorines, 6 sodiums. Over on the reactant side, we have 3 sodiums. So if we put a 2 in front of this, 2 times 3 gives you 6. 6 sodiums. That's good. So let's double check. We have 3 calciums. 3 calciums. We have 3 times 2, 6 chlorines. And we have 6 chlorines. We have 2 times 3, 6 sodiums. 6 sodiums. 2 times 1, 2 phosphates. 2 phosphates. That's all balanced. So for a double replacement reaction, you first switch the anions, putting different ions together. Then you use the charges of each ion to figure out how many of them there should be. Once you've done that for both of your products, you use the solubility chart to figure out if they are soluble or aqueous. Then you go through and balance the equation. Hopefully that has helped you a little bit with predicting products.